Okay, hello everyone. Today we're going to finish up chapter 4 in the calculus McGraw-Hill textbook, looking at applications of sinusoidal functions and their derivatives. So one of the classic examples that you might have seen already is a particle moving along a straight line. And why is that sinusoidal? Well, let's take a look. So the function is given here. Now, trig functions are periodic, which means they repeat themselves. So let's take a look at a little situation here. So if a particle, which is this little asterisk here, starts at a certain position at time 0, and suppose it moves in a positive direction and eventually reaches a maximum distance along that straight line, which in the graph would be starting at 0 and then going to the maximum, followed by returning to its starting position, which again from the maximum distance it would return back to 0 for the displacement. And then finally, if it were to continue along this path, going in a negative direction, opposite from where it went before, same distance, but in the opposite direction, and then a return back to the starting position, that's where you get the remaining portion. So again, at a displacement of 0, go to a maximum displacement in a negative direction, and then come back to the 0. So you get that complete sinusoidal function, and the x-axis is time, and the displacement is in meters. So one of the crucial things, or one of the things you may have to eventually determine, are things like this. For what values of t does the particle change direction? Now, there's a language that you should have heard of before called turning points. And the language is very appropriate to what we're talking about here, because the particle must eventually turn around from the maximum and go back from whence it started. Right? So to determine these t values here, so that one there, and that one there, well, it's a very straightforward process. You're looking for the max and min points, and as you know from derivatives, the derivative at these max and min points should be equal to exactly 0. Slope of the tangent would be 0 at those points. So if you can solve equations, that's what we're going to be taking a look at, and that's why it's important that you have your trig skills sharpened up. So the derivative of the displacement function has to be 0. So the derivative of the displacement function is 8. Derivative of sine is cos. Keep the angle the same, but then chain rule, taking derivative of 2t is 2. So we need to solve that equation when the derivative is equal to 0. So dividing both sides by 16 leads to this equation. Now this is something you should have done in previous math class, especially in advanced functions. It depends on how your teacher approached it, but you're looking at when is a cosine function of a particular angle equal to 0? Well, there's cast rule that's going to be involved, so that's something to keep in mind. So the cosine of a particular angle gives you 0. And you should remember that the angle that you have for cosine when it's 0 is pi by 2, so right here. So that's when your cosine is going to be 0, and also at 3 pi by 2, your cosine is going to be 0. So that's the particular angle. Whoops. That's the angle that is the key one. But because the algebra for the angle is 2t, the a here is going to be replaced with 2t, because we're looking for the time, not the angle, we're looking for the time. So the time, and you notice these are radian values, very important using radian values here. So that means 2t is equal to this radian measure of pi by 2, and also this measure of 3 pi by 2, and so on. So it's continuous. Now, what we wind up getting is dividing all of these values by 2 is the same as multiplying by a half. So half of pi by 2 is pi by 4. Half of 3 pi by 2 is 3 pi by 4. And then the pattern would continue. If you're wondering where this 5 came from, well, 1, 3, 5. There's odd numbers in there. So just to take a momentary break, just to quickly review some of these things that you should have seen from previous course in advanced functions, just to review where these patterns come from. So when you have multiple answers, and you will get this quite a bit, you need to be able to come up with a formula that represents your result. So in this case, time can be any one of these values in seconds. Okay, so it's important to write in the exact format. So ways to determine an arithmetic sequence formula: you can use your arithmetic sequence formula that you learned back in grade 11, or you can just use some common sense and logic. So n is going to represent an integer value, right? And if you have a pattern, for example, here, 2, 4, 6, then you could use this formula up at the top. A would be your first term. D is your common difference. So in this case, it would be 2. And then simplify algebraic, that would work. But sometimes it's a bit better to just look at patterns themselves. So this first number is a 2. The second number is a 4. And the third number is a 6. Well, those are just even numbers. So if you take 1, 2, and 3, multiply them by 2, you'll get the sequence values, 2, 4, 6. So your formula could be 2n, all right? So that's one way of getting a pattern which would work. And if you have an odd set of numbers, like this one here, 1, 3, 5, again, you could use this formula up at the top. Common difference would be 2, again. Or you can think of it this way. If you take an even number, any integer multiplied by 2 will give you an even number. If you subtract 1 from an even number, you will always get an odd number. But the interesting thing with this is that you can also take an even number and add 1 to it, and you'll also get an odd number. So either one of these patterns, 2n minus 1 or 2n plus 2, can represent odd values that you need for your pattern. So for example, back in this previous example, the 1, 3, and the 5 are all odd numbers. So in this little bracketed portion, since the other part is consistently pi by 4, this could have been 2n plus 1 or 2n minus 1. You decide. So as long as you specify that n has to be greater than or equal to 1, and n is an integer, that's all that's required. So we will have to play around a little bit with some of these patterns. All right. So in terms of the maximum velocity, now here you got to be careful because the word maximum can be a little tricky, but this is maximum velocity. So you got a couple of ways of looking at this. We took a look at some rates of change. So your rates of change for a maximum would occur at these special points. Oops, would have been down here actually. Called points of inflection. So you can find the points of inflection on the displacement function. That's one way to do it, so the slope of the tangent would be steepest at that point. And then find t substituted into the derivative, right? So that's your technique. Your derivative function, be looking for the maximum here. So that's step 1. Or I should say process 1. So that's one possibility. A more simplistic approach would be to think of it this way. Since your derivative of the displacement is equal to the velocity function, you're trying to, and this is the actual derivative of your displacement. Right? We've obtained that up here. So maybe a more simplistic way is trying to figure out what is the maximum this is ever going to be. Well, if you're pretty good with sketching things, this is just a cosine function. The amplitude would be 16. So it'd start off at 16 and end at 16, and you'd get your little cosine function. All right, don't worry about the period too much because you're more concerned about the maximums. All right, so logic will work, graph will work. Now, if you're looking at trying to find those points of inflection would occur at second derivative, setting that equal to 0. So that's technique number 2. Technique number 3, and there's different techniques. So these are 1, 2, and 3 different techniques here. Okay. So the point of inflection will give you the steepest slope. So to find the point of inflection, remember, use the second derivative, set it equal to 0, and you can find it that way. That will work. Or, as I just mentioned, you want the maximum velocity. So you can simply use your graph. And what's the largest value you're going to get for this function? Well, that will occur when this portion in here is equal to 1. All right, because that's the largest the cosine function is going to be. The max is going to occur when that is equal to 1. So when that occurs, your maximum velocity is 16. All right. So if this logic algebraically doesn't make a lot of sense, hopefully the graph will, because again, this function here, you're looking, if this is the velocity function, its maximum points will occur right there, those points. Now remember, you weren't trying to find the time, it was what is the maximum velocity. So the maximum velocity is 16 meters per second. So you have different ways of approaching this question. So the examples in the book will also give you a couple of samples, but just wanted to give you a variety. This technique is probably going to be familiar too, where you find the second derivative because you're looking for your points of inflection and set it equal to 0. That's one possibility, but probably a little bit more longer in the approach. This is probably the most simplistic way to do it, is number 3. Okay, so we already talked about the sequences. We're going to move on to another example, or another part of it. When is the particle at a position of 0 meters per second? So notice it has the word position. So position implies your displacement. So your displacement function was 8 sine 2t. So when is that displacement 0? And the question is when. So you're going to have to solve for t. Okay. So algebraically speaking, divide both sides by 8. And again, you have this little trick that this is just an angle. Just treat that like an angle. Right? Whatever it is, doesn't matter how messy it is algebraically, but if you can determine what angle in radians produces a 0 for a simple sine function, and in this case it's 0, pi, and 2 pi in radians, then you can use this concept to then find the t values because you're looking for the time. So that would imply that 2t is 0, pi, or 2 pi. Divide everything by 2, and you get this pattern. Now, I do suggest leaving the pattern here because it's important to see the actual pattern itself. So you'll notice there is a consistency of division by 2. You could also put in this little pi symbol in here if you wanted to. So 0 pi divided by 2, 1 pi divided by 2, 2 pi divided by 2. And the sequence numbers that you're trying to find that algebraic pattern for are 0, 1, 2. Well, not really much of an even or odd or anything for that matter. It's basically just cleaning things up. And so there's different ways of looking at that. So you can take the pi by 2, which is consistent throughout all the patterns, and just multiply it by a number n. And there's your pattern. So t is equal to pi by 2n, which will probably in the back of the book would look something like n pi by 2. It can be different formats. So it really depends on how the textbook prefers to indicate that. All right. Okay, and again, indicating that n is an integer. So the question again was when. So you've located the times. These are all the times, and these should be indicated in this case in seconds. Okay, and another part, when. So again, time. When is the particle at its maximum displacement from its origin position? So maximum displacement then means the maximum for the displacement function. And again, you don't have to get too complicated. So you're trying to find t, there's your displacement function. When is this function at a maximum? You can feel free to do a little sketch and try to work it out with a graph as long as it's roughly sketched out that way. But one more time, as we did before, you got to remember something with trig functions. Your maximums for trig functions in here will occur when this portion is equal to 1, okay, because that's the maximum value for sine. All right, if you think of your calculator, the largest number you're ever going to get for a sine and using your calculator, regardless of what's here in terms of the angle, the largest number you're ever going to get is 1. So the largest possible number you're ever going to get in this particular situation is 8. Now, if there was a bit of a transformation in here, for example, transformation up by 4, then you can have to use your trig logic. So again, this would be 1, because the maximum you're going to get for the trig is 1. Leave that in there for a second. So 8 times 1 will give you 8 plus 4, 12. So again, using a graphical technique could also get this maximum value that you're looking for, or just some simple logic, which is going on here. So your maximum displacement has to be 8 meters. Okay. You could, so that's the actual maximum displacement. Keep in mind the question was, when does this occur? So unlike that previous question that asked for maximum velocity, we do need to continue to find the t. So we found what the maximum displacement is, and we need that to set up an equation to now solve for t. So we have an equation we can solve for t. So dividing both sides by 8. Once again, trying to solve this equation, we have an angle for sine that is going to produce a value of 1. In radians, that will occur at pi by 2 and 5 pi by 2. Now remember, so we're looking at for a sine value of 1. So there's a little angle here, there's pi by 2. All right, so we don't want negative 1, we want positive 1. So we have to go a complete cycle all the way around and get 5 pi by 2, just to pick up a pattern. So we have 1 pi by 2, 5 pi by 2. Think of what the next number in the sequence would be. Correct, 9 pi by 2. All right, so again, we've replaced this angle, okay, temporarily, just to be able to come up with the radian values for the angles. But we need to actually find t, so we have to put that a value back in. So 2t is equal to these different values in the sequence. So 1 pi by 2, 5 pi by 2, 9 pi by 2, and notice it must continue on forever because that's the nature of sinusoidal functions, right? And particles, when they move back and forth, they just keep going on forever and ever and ever. So again, divide everything by 2 or multiply by 1/2 to get your actual pattern. You're looking for an algebraic expression for the 1, 5, and the 9. So here, you might be wondering where the 4n plus 1. So these are odd numbers, but they're odd numbers in terms of multiples of 4, not multiples of 2. So 4, odd value of 0. So think of 0, 4, 8, and so on. So 0, 4, not a good 0, but my pen's going to cooperate. 0, 4, 8. But I actually want 1, 5, 9. So I have to add 1 to each one of these. So this will give me even numbers, multiples of 4. If I add 1, I get that. Now again, you could use the sequence formula to come up with this formula here, but this would be the basis of finding the algebra. And then the common part of the sequence is the pi by 4. And you can leave it in that format. I'm okay with that, but the textbook will have some interesting, more algebraic ways of simplifying. All right, so just keep that in mind when you're looking at the solutions. So this is the other way to do it. You can use this formula here to plug in your values, and just to show you how different it would look. So your common difference is 4. Your a value would be 1, and then you would move on from there to determine your formula there. And you notice that this formula is 4n minus 3. So it doesn't matter which formula you're going to be using in here. This blue one that you notice, this is a distributive property of what's going on up here. Okay, so you got to be mindful of that this is just distributive property. So regardless of what the pattern is, You got to be mindful that there are different ways of coming up with that pattern, and the textbook will have some interesting ways of coming up with it. So as long as your pattern works, that's the most important thing. All right, so try the best you can. All right, so the last question we're going to be taking a look at is a slight variation on trig as well. An object is suspended from the end of a spring. Now, why is this sinusoidal? Well, when an object is on a spring, that's going to look kind of funny, but we'll kind of pretend anyways. So the object is the thing in red. So it is going to start off, and eventually it's going to reach a maximum distance from the ceiling. And then it's going to bounce back to its resting position. And then it's going to spring up somewhat. So it'll have this repeating pattern of going down and up, down and up. And it'll have kind of like a center position where that's the position at rest, so to speak, when it first started. Right? So that's why it's kind of sinusoidal. So it's going to have an equal distance there and there. Now that might not be perfectly physically true, but we're going to pretend for this part anyways. So you have a displacement function from equilibrium. So equilibrium means it hasn't moved up, it hasn't moved down. That's important to note. So you have a displacement function given to you. You're asked to determine a function for the velocity and the acceleration of the object. So if we have a displacement, how do we find a velocity function? Correct, it's a derivative. And then the acceleration would be a second derivative. And one of the things that this question wants you to do is to show that the second derivative of the displacement with respect to t is negative 100 pi squared s. And that basically means that the second derivative is equivalent to this expression here. Now, if you're wondering well, how that came to be, well, the s is a representation of your displacement. So you have to prove algebraically that this works. But we also have to find the velocity and an acceleration function. So the velocity and acceleration function are pretty straightforward. So as I talked about, velocity is going to be your derivative of the displacement, and the acceleration is going to be the second derivative of the displacement or the derivative of your velocity function, whichever way you want to look at it. So those expressions are pretty easy. So your derivative of your displacement is pretty straightforward. So again, just to make sure we're clear on that, keep the coefficient of 8. Derivative of sine, cosine, keep the angle the same, but then the chain rule requires us to take the derivative of that angle expression, and pi is a constant. So derivative of t is 1 times 10 pi is 10 pi. All right, so that's your velocity function. You're also asked to find the acceleration function, so a good idea to simplify this before finding a derivative. So your acceleration is the second derivative, or the derivative of the velocity function. So again, this is just a constant. All right. Now, if you're wondering where all this came from, well, eventually you're going to get a chain rule in here that needs to take the derivative of the angle, which is going to give us another 10 pi. 10 times 80, 800. And if you're wondering where the negative came from, derivative of cosine is negative sine. Keep the angle expression the same, exactly the same. So we've accomplished 2 of the parts of the questions, find the velocity, find the acceleration. And the last thing was to show that the second derivative is equivalent to negative 100 pi squared s. Well, we do have the second derivative function here in front of us, and a simple little common factoring, in a way, technique. So if we split the 800 into negative 108, and why would we do that? Well, because we want the coefficient here to be negative 100. We already have the pi squared. If we connect the 8 mathematically as multiplication by the sine function part, multiply it by this here, and we identify it as a separate function, well, we've met the requirements of the negative 100 pi squared up at the top. S must be equivalent to 8 sine 10 pi t. 8 sine 10 pi t. And we have, whoops, met the requirements of this question. So we've done the acceleration, the velocity, and proven that the second derivative is actually in fact equal to negative 100 pi squared s. This would be your most challenging part of the unit. So do spend quite a bit of time working with this. And you do have a decent number of practice questions. Feel free to do whichever ones you like to make sure you understand the concepts.